We want to talk a little bit more about some more linear transformation stuff. So let's suppose that T maps Rn to Rm is a linear transformation. So here's an image, or a picture, the way we think of it. We just think of Rn and Rm, since they're just big flat spaces, we just draw rectangles to represent them. So Rn is the domain. The domain is where we start. So the domain is Rn. We'll refer to Rn as n-dimensional space. We'll say this is n-dimensional. When we say something is n-dimensional, oh yeah, the dot is a vector. Yeah, we think of it as bird's eye view, so it's a little arrow and it's pointing directly out at the camera. That's why it's not like at an angle. So the domain is Rn, or n-dimensional space. When we talk about the dimension of a vector space, when we talk about the dimension of a vector space, that means that there are n vectors in a basis for the space. So that means any basis has n vectors in it. So if a space is n-dimensional, that means the basis has to have n vectors in it. We refer to, in this case, we'll refer to Rm as the codomain. In the past, we heard about domain and range, but we have to separate the two concepts. So Rm is the codomain. And so this is m-dimensional space. So that means a basis for Rm will have m vectors in it. We want to separate out the codomain of the transformation and the range of the transformation. The range of the transformation is the set of the images of all the vectors in Rn. So the range of the transformation is the set of images. So the range of T is the set of images under the transformation T. The range is a subspace of Rm. So the range is what we call a subspace of Rm. The range could be all of Rm, or it could be some proper subspace of Rm. So we should point that out. So even though it's a subspace, it could be all of Rm. If the transformation is onto. If the transformation T maps Rn onto Rm, that means we're covering everything in Rm. The range of T is equal to the codomain. So we need to talk about, since the concept of subspaces has come up and the concept of basis has come up, we need to talk about how we describe subspaces. So here's a big idea. How do we describe subspaces? To describe a subspace, we need to have a basis. The subspace, the span of a set of vectors is always a subspace. So we always describe subspaces as the span of a set of vectors. The span of a set of vectors remember, when we talk about the span of a set of vectors, we're talking about all the linear combinations of the set of vectors. So the span of a set of vectors is the set of all linear combinations of those vectors, and that will always be a subspace. What we are going to, so the set of vectors could be what we call a spanning set. And what we want to do is we want to whittle down our spanning set into a linearly independent spanning set. A basis for a subspace is a linearly independent spanning set. So we're going to describe subspaces by finding a basis for the subspace. So let's take our previous example where t of x is equal to so a was, that was a whole page ago. I can't be expected to remember something for a whole page. So t maps, if a is, so a is 3 by 2, so t is mapping R2 to R3. Let's find a basis for the range of t. I realize that by phrasing it that way, I'm implying that the range of a transformation is always a subspace, and it is. So you can just take my word for it now. So let's find a basis for the range of t. So since we have the matrix of the transformation, we could say that T is the span of the set of vectors. That's the columns of A. So T, oops, range of T. The range of T is going to be the span of the columns of A. I want my basis to be written as a set of vectors. So I don't want to say A is a basis because A is a matrix and A is not the basis. I need a set of vectors to be the basis. The columns of A is a set of vectors. So the range of T is the span of the columns of A. Notice that these two vectors are linearly independent, and every vector in the range of T is a combination of these two vectors. So here's a linearly independent spanning set. Notice that there are two vectors in the range, in a basis for the range of T. There are two vectors in a basis for the range of T, so we could say that the dimension of the range of T is equal to 2. Now we've taken that whole lot of stuff that you have to remember and we've just added to it. So now there's even more stuff that you have to remember. But you only have to remember all of it all the time in perfect detail and make sure you get the words right. Otherwise, I give you 0 points and make you do the quiz again. And then you get really mad at me. That's what I said. And then I'm like, oh, not exactly. You said A is linearly independent. It's like, oh, the columns of A are linearly independent. And he's like, well, why you gotta be so picky, Leach? I'm like, well, because we're talking math, and math is a very picky language. So what we see is that T maps R2 onto or maps R2 to a two-dimensional subspace of R3. This makes sense. This should make sense because we start off in R2, we end up in R3, but since we only started with a two-dimensional space, it makes sense that we could only end up with a two-dimensional space. The range can't be bigger than what we started with because we start with, at most, 2 linearly independent vectors. We're not going to get more than 2 linearly independent vectors in the image because we have a transformation, and the transformation will respect your linear combinations. How's everybody, okay? Let's take a look at another example. I'm going to grab another matrix. Oh, I'm going to first realize that I thought I had another matrix that I could use open in a tab, but I didn't. All right. Let's look at another example. Let's suppose that T maps, we'll fill in these, is given by so here's the matrix I want to use. A is going to be 1, negative 2, 3, 2, 0, negative 5, 0, 4, negative 11. So A is a 3 by 3 matrix. So that means T maps R3 to R3. First thing we want to notice is that we are looking at a matrix. When we're looking at a matrix, we should start thinking immediately, what's the reduced echelon form of the matrix? So let's grab the reduced echelon form of this matrix. 1, 2, 0, negative 2, 0, 4, and then 3, negative 5, negative 11. Close the row, close the matrix, close the command. So what we see is that the reduced echelon form, we have two pivots in the first row, first column, second row, second column. That third column is a linear combination of the first two. The columns of A are linearly dependent. So A, we find the reduced echelon form of A, and it was 1, 0, 0, 0, 1, 0, and I already forgot. Negative 2, 1, 0. One thing to note, the reduced echelon form is how we find the pivots, but it's A that has the pivots. Now here's a tricky thing. The pivots are positions, not numbers in the original matrix. Even though there's a 0 in the second row, second column, that's where the pivot is, as the reduced echelon form tells us. So A has a pivot in the first row, first column, and the second row, second column. It doesn't matter that there's a 0 in the second row, second column of A. That's where the pivot is, revealed by the reduced echelon form. We don't say the reduced echelon form does not have a pivot in every row. A does not have a pivot in every row. So we see a lot of stuff going on here. We want to think about everything, but only write what we need to write. So we see that A does not have a pivot in every row. So that means some stuff to us. That means the columns of A do not span R3. The columns of A span a two-dimensional subspace of R3. I'm going to add that little note. We can also talk about the equation. The equation AX equals B is not consistent for all B in R3. The upside down A is an abbreviation for all. Or we could say AX equals B is inconsistent for some B in R3. These are all the things that should just automatically occur to us when we see that A does not have a pivot in every row. We can see that this transformation, since that's come up in the beginning, the transformation is not surjective, it is not onto. We also see that A does not have a pivot in every column. So let's talk about the column stuff that we notice. As a set of vectors, the columns of A are linearly dependent. Oops. In particular, we can see that A3 is negative 2A1 plus 1A2. One of the ways to characterize a linearly dependent set is that one of the vectors is a linear combination of the others. So if I call the vectors in A1, A2, and A3, then we can see that A3 is negative 2 times A1 plus A2. That's not what we would want to use. We would, since we're given a matrix, we would want to use A does not have a pivot in every column. Therefore, the columns of A are linearly dependent. What this means in terms of the equation, since the columns are linearly dependent, we know that the homogeneous equation, AX equals 0, has a non-trivial solution. That's what we should go for when we have a linearly dependent set and we want to say something about an equation. We don't want to say there is a non-trivial solution, because my response, as some of you saw, is what equation? So notice that if I just drop the matrix A, there's no equation running around yet. We could also include that if AX equals B is consistent, then there will be many solutions. We should also note that if AX equals B is consistent, then there are many solutions. We're not guaranteed solutions until A has a pivot in every row, which is the row department, not the column department. And right now we're looking at columns. We can also say that this transformation is not one-to-one, or not injective. I should put the other words, which is 1-to-1. So 1-to-1 means that you don't have two vectors going to one vector. That would be many to one. So let's write that definition, because we loves us some definitions in math class. So injective injective means that you don't have the images, two different vectors in the domain mapping to the same vector in the codomain, or the range. The best example, oh, I wrote this totally backwards. How do you guys let me get away with this stuff? As with a lot of things, the best example is an example of not this. So for example, x squared is not 1-to-1. Because f of 2 is equal to 4, and f of -2 is also equal to 4. There's two inputs that give us an output of 4. One way to think about this is that when you're looking at the image, you know where it came from. 1-to-1 means we know where the image came from. So if I said x squared equals 4, we don't know if x is 2 or -2. We don't know where that 4 came from. But if we have a 1-to-1 function, we know where that output came from. In a 1-to-1 function, we know where the image came from. So for example, as a function, f of x equals x cubed is 1-to-1. If f of x equals 8, then we know x is 2 and no other. We know where the 8 came from. If f of x is equal to 8, then x equals 2. So we can see if T is a transformation given by this map, multiplication by this matrix, since A does not have a pivot in each column, that means T is not injective. T maps lots of vectors onto one image. So let's draw a picture of what's going on in this transformation. So we start with our domain of R3. And we're mapping to our codomain of R3. But we know T is not onto because A does not have a pivot in every row. So we start with everything in R3. The range is going to be smaller. We're not going to get everything in R3. Everything in R3 is not the image of some vector under the transformation T. We know we don't get everything, but we know what we do get. What did I use? Oh, yeah. Ranges are blue. So we know that the range of T is a two-dimensional subspace of R3. If it's a two-dimensional subspace of R3, that means there are going to be two vectors in a basis. Now, once I tell you what these two vectors in the basis are, that will instantly reveal how I know that there are two vectors in the basis and how to pick out those two basis vectors for the range of T. Once I tell you this, all of linear algebra will snap into focus and you will all instantly understand everything that goes on in this class. This is going to be the singularity moment. Once I do this, everything will make perfect sense for this whole class for the rest of the semester and for the rest of your life. But as long as I only do this right now, I have to tell you right now what the basis for the range of T is, what two vectors form a basis for the range. If I do this right now, then linear algebra will instantly make sense for the rest of the semester, it'll just all become perfectly clear. So here are the two vectors in this basis. Oh dang, look at the time. We're gonna have to come back to this. I guess we don't get instant understanding. If you've been in my class before, you knew that was coming. But what I'm doing here is what I want you to do is I want you to think, what are the two vectors in the basis? How did he know that this is a two-dimensional subspace of R3? How do we know that there's going to be two vectors in this basis? And what two vectors are they going to be? Well, that's what I want you to find out. What vectors can we get rid of is what we're thinking about. We got a spanning set that's 3 vectors, and I want it cut down to 2 vectors because one of them we don't need. You'll totally understand linear algebra. It's just going to be a lot more work than it would have been. And I'm totally just kidding. So it's always going to be a lot of work. That's what makes it fun. All the work that we have to put into it. And that's what makes it rewarding. All the work that we have to put into it. That's what makes it frustrating. All the work that we have to put into it. Especially when the guy that you hired to just tell you what the answers are isn't just telling you what the answers are. Michael, no, you're wrong for this reason. No, you're wrong for this reason now. And then like 6 submissions later, finally it's Michael, yep, 4 out of 4. All right. That's what I want you to work on. So we're actually expanding into subspaces. So I know some of you have started work on your chapter 2 homework already. So in chapter 2, there's a lot of stuff with matrix operations. And then chapter 2.8 and 2.9 is where we start talking about subspaces, which is one of the difficult things about this class, because we talk about all of it all the time in all of its detail. And so you have to remember everything all the time in perfect detail. And that's what makes this class frustrating, but that's also what makes this class fun. Bull Durham style. Fun, damn it. All right, that's going to do it for today. That's going to do it for this week. I'm going to stop recording. So see you later, YouTube.